Hello everyone and welcome to this new video on Module 4. In this module, we will be diving into system modeling. The aim here is to introduce you to the system models that play a critical role in the requirements engineering and system design process. By the end of this video, you will have a solid understanding of what system modeling entails and how graphical models can be used effectively to represent various aspects of software systems. We will explore why using different types of models is essential and how these models provide different perspectives on a system. We will discuss four fundamental perspectives of system modeling: the context modeling, interaction modeling, structure modeling, and finally behavior modeling. Each of these offer a unique insights into the systems designs and help create a comprehensive representation. And as always, to ensure we have grasped the concepts covered, I will end the video with a review question to help us reflect on and solidify our understanding. So let's start. Let's begin with an essential question. What is system modeling? System modeling is a process of developing conceptual blueprint that provide diverse perspective on how a system operates. These models help capture the structure, behavior, and interactions of a system without diving into all the fine details. It is important to note that when we talk about modeling, we are referring to an abstract model, meaning they include only the most important elements, omitting finer details to keep the representation manageable. To help you see this, consider a movie trailer versus a full movie. Trailers give you an overview with the main highlights, characters, storyline, just to attract viewers. But it doesn't show all scenes or all the details in the movie or the scenario. Similarly, system modeling provide an abstract representation of the system, highlighting essential components and functions without detailing every part. So keep this in mind as we dive deeper into the different types of system models and how they contribute to understanding and designing complex software systems. Our second question, why do we need system modeling, or why is it important? The answer lies in the necessity to understand complex systems, whether they are existing or not yet developed. For current running systems, system modeling captures their essence and become pivotal during the requirement engineering phase, helping stakeholders and the developer comprehend existing functionalities. Stakeholders can use models to communicate how the system currently operates to developers, while developers can utilize these models to identify the system's weaknesses and strengths. When it comes to future systems, system modeling is just as important. We create models to visualize and facilitate design proposals, which then serve as a comprehensive documentation for eventual system implementation. So, in brief, system modeling acts as a forward-thinking approach that ensures everyone involved has a clear roadmap, enhancing communication and efficiency throughout the development process. Actually, we may need to develop different models to represent a system from various perspectives. And let's first ask, why do we need multiple perspectives for system modeling? The answer lies in the complexity of systems. Complex systems cannot be fully captured or understood with just one model. Each perspective sheds light on different aspects of the system, ensuring a thorough understanding and more effective development. Different models help to clarifying how the system interacts with external elements, understanding communication within and outside the systems, visualizing the structure and data organization, illustrating system response to events. Now let's break down these perspectives. The first one is external perspective, or sometimes we call it context perspective. This model shows the system context or environment. The second model is, or the second perspective is interaction perspective, which focuses on the interactions between the system and its environment or among system components. Structural perspectives that models the organization of the system and the structure of data processed. And finally, behavioral perspectives that capture the system's dynamic behavior and the response to different events. Using these different perspectives allow for a comprehensive, multidimensional understanding, ensuring that no critical details are overlooked during system analysis or design or even development. To develop these models, we will use graphical notations focusing on the diagrams defined in the UML or in the Unified Modeling Language. Why do we focus on diagrams or graphical notations to represent our models? Well, in today's modern era, our primary language is the visual one. It helps in breaking down complexity and making things more relatable. As I mentioned in the previous slide, we will use UML to represent our models. UML's graphical notations allow analysts and stakeholders to gain a clear and profound understanding of a system's functions and communicate their ideas with precision. Think of UML as a toolbox with 13 different tools. However, in most cases, only 5 are commonly used. First, we have activity diagram, which illustrates the flow of operations and data. Then there are use case diagrams, mapping out how users interact with the system. Sequence diagrams come next, detailing the interactions and exchanges between actors and system components. Class diagrams reveal the relationships between different object classes. And finally, state diagrams show how the system responds to various events. These 5 UML diagrams provide a powerful framework for modeling and understanding complex systems in a fraction of the time. It is important to note here that system modeling is not a complete representation. It intentionally leaves out details to maintain simplicity and focus. Let's begin with our first type of model, the context model. Think of context models as blueprint of a system surroundings, clearly defining what belongs to the system and what doesn't. These models act like maps outlining the boundaries of the system and showing its interactions with external environments. It's more than just code and software. It is about understanding the connections between the system and the people, organization, and other systems it interacts with. Why are these models essential? Because they provide clarity on where a system fits in the larger pictures and help identify potential dependencies and interactions that might affect the development and functionality in some times. Now, in some cases, these boundaries are relatively straightforward. For example, when replacing an existing system, whether it is manual or computerized, the environment often remains the same, making it easier to map out the boundaries. However, context modeling becomes more complex in other cases. For example, when dealing with systems like patient information and the prescription management tools, similar to MintCare that we discussed in our first module. In such cases, it is not always clear if the system should handle, for example, all patient data internally or if it should rely on external database and systems for information retrievals. This uncertainty requires deeper analysis to define what the system will manage directly and what it will interact with. Let's think about Medicare system in more details from the context perspectives. In the case of Medicare system, it interfaces with several external systems. For instance, it exchanges data with an appointment system and patient record system to manage scheduling and patient details. Additionally, it connects with the management reporting and hospital admission systems to support administrative functions. The system is also linked to a statistics system that gathers data for research purposes. Lastly, it interacts with a prescription system to create and manage patient prescriptions. This type of visualization is called a context diagram or an external systems diagram. While it is not officially part of UML, it serves as a high-level representation to show how a system interacts with external entities. From these examples, it becomes clear that context models are powerful for visualizing which external systems interact with the main system. However, they don't detail the nature of these interactions, such as how data is exchanged or specific connectivity. To gain a full understanding of system interactions, it is important to use context model in combination with other detailed models. One of the UML diagrams used in context modeling is the activity diagram, which includes more details compared to the previous context diagram. In this slide, I will walk you through an activity diagram showing the Medicare system's involvement in a critical mental health care process, which is involuntary detention. As you can see, here the process starts with a filled circle indicating the beginning of the activity diagram. The first activity, represented by a rounded rectangle, is confirmation of the detention decision. Then we will have an arrow. This arrow shows or illustrates the workflow in general. Next, we can see a solid bar that splits the flow into parallel activities, which are inform patient with their rights and record the detention decision. And this will need a connection to the Medicare system. After running all these activities in parallel, we can proceed forward to the decision node. This decision node will check whether the patient is dangerous or not. In case the patient is dangerous, I will need to find a secure place. If this secure place is available, then I will go ahead and transfer it to this secure hospital. If not, this will need from you to contact with a police station. In case the patient is not dangerous, then the detention can be done in a regular hospital. This is why it will lead to admit to a regular hospital, and this will need a connection with the admission system. After getting done with all these activities, this will lead to another solid bar that will lead to a new activities that can be done in parallel, which are informing the social care, informing relative, and updating the register. Updating the register will need another connection with the system, which is Medicare. All this will lead to another solid bar, which will lead to the end of this activity. And the end of this activity diagram is indicated by a solid circle, and this solid circle inside another circle. This activity diagram provides more comprehensive details about the entire process compared to the previous context diagram, giving you a clearer picture of how the system interacts within the workflow. Now let's move into the second perspective or model, which is the interaction model. Every system needs a way to interact with its surroundings. This could include interactions between system and its users, connection with other software systems, or different parts of the same system. Understanding how users will engage with the system is crucial for meeting their needs. You need to understand what inputs come from the user and what outputs are expected. Planning system-to-system interactions help identify potential communication issues. For example, if you call a module, you need to understand its interfaces, including what argument is required and what it will return. Additionally, modeling interaction between components allow us to assess if the system will meet the required performance and reliability standards. To model these interactions, we primarily use two UML diagrams, the use case diagram and the sequence diagram. Use case diagrams provide a high-level view of the interactions between users and the system, while sequence diagrams offer a more detailed look at the step-by-step flow of interaction within the system. In practice, using both diagrams together provide a comprehensive understanding of system interactions at different levels of details. Use cases diagrams are originally developed to support requirement elicitation, and now they are an essential part of the UML framework. Each use case represents a specific task involving external interactions with the system, whether it is initiated by a person or another system. One of the strengths of use cases is that they offer dual perspectives, a visual overview that shows the interaction at a glance, and a detailed textual description that breaks down steps of each interaction. This combination helps ensure that everyone involved in the development process, from stakeholders to developers, can understand and agree on how the system should function. It is important to note that actors in use cases are not limited to just people. They can also represent other systems that the main system interacts with. This flexibility makes use cases valuable in modeling complex interactions and defining clear system boundaries. In its simplest form, a use case is represented as an ellipse, while the involved actors are depicted as stick figures. For example, here the data transfer in Mintcare system. We see two main actors, the operator handling the data transfer and the patient record system itself. The stick figure notation is used to symbolize both human interactions and interaction with external systems. Typically, use case diagrams feature a line without arrows, as arrows in UML indicate the direction of message flow. In this example, arrows are used informally to demonstrate that the medical receptionist initiates the process and data flow to the patient record system. Sequence diagrams are part of the UML and are used to model the interactions between the actors and the objects within a system. Usually it shows the sequence of interactions that take place during a particular use case. This is why it contains more details, as I mentioned previously. Let's see an example, which is view patient information in Mint Care system. In sequence diagram in general, we start by listing the objects and actors involved along the top of the diagram with a dotted line drawn vertically from these objects. We have here the medical receptionist as an actor, and the objects are patient information, meant care database, and authorization object. These rectangles along the dotted lines making the object's lifelines or involvement duration. And then a notated arrow display interaction. Note that the sequence diagram is read from top to bottom. We can see here that the medical receptionist initiates the retrieval of patient information by invoking the view information method in an instance P of the patient information object class. The patient's identifier BID is provided as a parameter to specify the requested information. The instance P communicates with the database to obtain the requested information, so it sends the information, the BID, and the user ID. The database verifies the authorization of the receptionist through an authorization system. It checks whether the receptionist has the necessary permissions to perform the requested action or not from the returning of this call. Now we will have an alternatives which are donated by an alt box with conditions in brackets and different interactions option divided by a dotted line. So we have here two options, authorization OK or authorizations fails, and we'll have different return. If the authorization is OK, I will return the patient information. If not, I will return an error showing no access to this information. Note that the solid lines in the sequence diagram represent a call, indicating a direct interaction where the sender waits for a response from the receiver before continuing. The dotted line represents a return message, so the sender does not wait for a response and can continue processing. Now let's talk about the third model, which is structural models. In software development, a structural model represents the organization of a system, detailing its components and how they relate to each other. These models are essential for visualizing and understanding the system's architecture. For example, consider a hotel booking system. A structural model would show components such as reservation system, user interface, payment processors, database. It would illustrate how these components are connected and interact with each other to form a cohesive system. Structured models can be classified into two types, static models and dynamic models. Static models which illustrate the system's design structures, showing components and their relationships, while dynamic models depict how these components interact and behave during the system executions. Structure models are typically used when discussing and designing the system architecture. By creating these models, developer and stakeholders can better understand the system's structure, ensuring a clearer path during development and maintenance. One of the most popular diagram used for the structure model is a class diagram. Class diagrams are used when developing an object-oriented system model to show the classes in a system and the association between these classes. It can be represented at a different level of details. To start, let's look at a simple example of a class diagram illustrating the relationship between patient and their patient record object. As you see here, the class name is written inside a box. The line connecting these classes represents their association, and in this case, it is labeled as 1-to-1, indicating that each patient has one record and each record is linked to a single patient. In general, associations in class diagrams can be one-to-many, one-to-one, or even one to a specific number, as shown in this example. We have here patient. The relation between patient and general practitioner is many to one. We can understand that the patient is can be referred by a single practitioner, but the general practitioner can refer multiple or many patients. The relation between patient and consultation is many to many. Patient can attend multiple consultation over time. And at the same consultation, multiple or many patients can be involved. Again, this is not your decision. This is a business decision. They assume that there is a, let's say, a group therapy. This is why they assume that the relation between consultation and patient is many to many. Same here, in consultation, we can prescribe multiple medications. In medication, certain medication can be prescribed at multiple consultations. We indicate the many by this asterisk, means from one to many. Consultations and doctor. We can understand that doctor can attend multiple consultations, and consultations can have maximum of 4 doctors. This is why we have a specific number here from 1 to 4. Class diagram can include more details by showing class attributes and methods. Let's see this. In consultation, for example, I have the list of these attributes. I start with the name of the class, followed by the attributes that I have. Who is the doctor that does this consultation or run that consultation, the date, the time, the clinic, whatever the attributes that you have, followed by the methods or function that can run through this object, like having a new consultation, prescribe certain medication, record notes, transcribe, or whatever. So, I mean, and we will build all these details for all the classes that we have, not just for one of them, but I will include all these details for all the objects that I have. Let's introduce a new concept, which is generalization. Generalization as a technique is not unfamiliar to you. It is something we use daily to manage complexity. For instance, when I say vehicle, you immediately understand that I am referring to an object that can transport us from one place to another. However, vehicle is a very general term. Vehicle is a very broad term. It could mean a water vehicle, a land vehicle, or an air vehicle. Each of these categories is still quite general. For example, a water vehicle could be a boat or could be a ship. An air vehicle could be an aeroplane or a helicopter, while a land vehicle could be a car, a motorcycle, a truck. Even within these categories, there are further distinctions, like car could be a gas car or an electric car. And you can continue adding more specific details, such as a model, such as a make. So instead of learning the detailed characteristics of every individual entity, we group these entities in more general classes like cars here or vehicles, animals, houses, and then understand the shared characteristics of these classes as a whole. In diagrams, as you see here, generalization is represented by an arrowhead pointing upward towards a more general class. Now let's look at an example from Mentcare system to illustrate this concept further. Here we can see the generalization hierarchy showing that both Hospital doctors and general practitioners can be generalized as doctors. Within the category of hospital doctor, there are three types. Trainee doctors who have just graduated from medical schools and need supervision. Registered doctors who can work independently as part of consultants team. And consultants who are senior doctors with full decision-making responsibilities. It is important to understand that the attributes and operations associated with higher level classes are also inherited by lower level classes. These lower level classes, known as subclasses, inherit attributes and operations from their super classes. For instance, in the doctor class, we might expect attributes such as name, phone number, email. These attributes also apply to both hospital doctors and general practitioners classes. Lower level classes then add more specific attributes and operations that are unique to them. For example, a hospital doctor might have attribute like a staff number or a pager number, while a general practitioner wouldn't have a pager but might need an attributes for an individual practice address, for example, since they are working independently. Objects in the real world are often made up of different parts. Think of a car that is made up of wheels, engine, seats, and other components, all working together to form the whole vehicle. UML provides a way to represent this special type of association between classes called aggregation. Aggregations means that one object, known as the whole, is composed of other objects, called parts. In UML, aggregation is shown by adding a diamond shape to the line linking the classes, next to the class representing the whole. For instance, you see here a patient record from a Medicare system. The patient record is composed of the patient class and an indefinite number of consultation instances. This means the record holds both the patient personal information and individual records of each consultation with a doctor. This representation helps show how different components come together to form a complete system. The last model I will discuss today is a behavioral model. These models focus on illustrating the dynamic behavior of a system during execution, showing how it responds to external stimuli. Behavioral models highlight the system's interactions and how it reacts to various inputs or events. Stimuli can generally be categorized into two types. Data stimuli, and we call this model data-driven models. In this type, the system processes incoming data as it arrives. For example, think of data processing system like a phone billing program that collects call data, processes it, and generates monthly bills. Or this stimuli could be an event, and we call this model event-driven models. In this model, the system responds to specific events that trigger processing. An example would be a landline phone system, which responds to events like lifting the handset or pressing a number key. The system performs corresponding actions, such as generating a dial tone or capturing the phone number dialed. While events may sometimes come with data, that's not always the case. Data processing systems rely mainly on data input to drive operations, while real-time systems are more event-driven and prioritize responding to event over data processing. Let's talk about these two models in more details. Data-driven models are essential in understanding many business systems. These systems are often primarily driven by data, meaning their operations and processes are controlled by the data that flows into them, with minimal focus on external event processing. Data-driven models are great for showing the sequence of actions a system takes when processing input data and generating the corresponding output. This step-by-step visualization is invaluable during the analysis of requirements, as it helps illustrate the complete process from start to finish. In other words, if you are trying to understand how a system transforms input data into output, data-driven models provide a clear picture of that workflow. This comprehensive view can aid both analysts and stakeholders in identifying system requirements and any potential improvement in the process. Let's look at an example from the insulin pump case study. We often refer to the diagram that describes the flow of data as a data flow diagram, DFD, which was one of the earliest graphical software models. Although UML doesn't officially include DFDs, we can use activity diagrams to represent them effectively. In these slides, we have an activity diagram that showcases the operation of an insulin pump. The processing steps are represented as activities, which is this round rectangles, and the data that flows between these steps are shown as an object, which is this regular rectangles. As shown here, the process starts with the blood sugar sensor data, followed by the get sensor value activity. This produces collected sensor data, which moves into the compute sugar level activity, resulting in the blood sugar level data. Next, the calculate insulin delivery activity determines the required insulin amount, producing insulin requirement. Then it will feed to the calculate pump command activity, which describe how the pump should be controlled. The output will be the pump control command, which will be sent to the pump in the control pump activity, leading to the final step where the correct insulin amount is injected into the patient. This data, or as you see here, each activity waits for the required data, and once available, it triggers the start of that activity. This data-driven sequence is why we refer to it as a data flow diagram. Note here that also we can use sequence diagram to represent the data flow diagram instead of this activity diagram. Now let's cover event-driven modeling, which shows how a system responds to external and internal events. The key idea here is that a system has a finite number of states and that certain events or stimuli can trigger a transition from one state to another. Because of this, event-driven modeling is closely related to state diagrams. These diagrams are a great UML tools for illustrating the different states of a system and the events that cause transition between these states. For example, think of a landline phone switching system. It responds to events such as receiver off hook by generating a dial tone. Another simple example is a traffic light system. When the timer runs out or a pedestrian pushes the button, the light changes from green to yellow, then to red, showing the transition based on events. Event-driven modeling helps visualize and understand how a system reacts to various events and changes, making it essential for designing responsive and dynamic systems. On this slide, we have an example of a state diagram for a simplified microwave oven. I won't go through all the states, but let's look at a few key examples to understand how this works. We start here at the waiting state, where the oven displays the time. When a switch is pressed to select either half power or full power, you will go to the corresponding states and will set the power to the appropriate value. If it is full power, for example, I will set power to 600. If it is half power, I will set the power to 300. If you are in one of these states and the user presses the numeric pad to set the timer, that change the state to a set time state. If the door is opened during this process, the system will do transition to a disabled state, where it will stay until the door is closed. Once the door is closed, a transition will happen to the enabled states. Take a look at the rest of the states on the diagrams for a complete view. This should help solidify your understanding of how state diagrams illustrate the various states and transition within a system. And I encourage you also to see more examples on the textbook. The last topic that I will cover in today's video is model-driven engineering, or MDE. This is a different way of developing software where the main focus is on building models instead of writing code. The programs that run on computers or other devices are then automatically created from these models. The big idea behind MDE is to make software development easier by allowing engineers to think at a higher level. This means they don't need to worry as much about the details of programming language or how the program will run on different platforms. For example, if you were designing an online shopping application with MDE, you would create detailed models showing how the app should work, including how users add items to their cart and check out. The software for the application would then be generated from these models, so you wouldn't have to write all the code by your hand. MDE is somewhat similar to how generative AI works. When we describe software to tools like ChatGPT and receive code as an output, the main difference here is that MDE relies on more formal models, not just verbal descriptions to create a fully functioning software. So MDE help engineer spend more time focusing on solving the main problems rather than getting stuck in the details of coding and technical setups. Now let's discuss an important question. What are the advantages and disadvantages of model-driven engineering? I would like you to pause the video for a moment and think about both the positive and the negative aspects of this approach. Alright, let's start with advantage of MDE. One major benefit is that it allows systems to be considered at higher levels of abstraction. This means engineers can focus on solving complex problems without being bogged down by programming language syntax or platform-specific details. For example, if you are designing a shopping application, MDE enables you to create models outlining workflow and interaction without initially worrying about how to code it all. All what you need just to draw the model, feed it to an MDE, the output will be the running software or the running code. Another advantage is that generating code automatically can make it cheaper to adapt system to new platforms. Imagine having an app built for Android that you need to make it available for iOS. With MDE, code generation from models help you quickly adapt the system for a new platform without having to rewrite it from scratch. Because I have the same model. I will feed the model for MDE that will generate iOS code. The same model, I will feed it to another MDE that can generate an iOS code. Now let's move to the disadvantages. While MDE models are great for visualizing and planning a system, they might not always translate well into real executable code. For instance, a model for complex financial system could look perfect on paper, but may need significant adjustment during implementation to handle real-world performance issues. Additionally, the savings from engineering code might be outweighed by the cost of developing translators for new platforms. If you are building software that needs to run on various types of devices, maintaining different code generators for each platform could end up being more costly than coding directly for each one. I hope that these points cleared up the advantages and the challenges of MDE, especially when it comes to practical implementation. I believe that's all the material I wanted to cover with you today. To wrap things up, let's go through a review question to put some of what we have learned into practice. Imagine you are the chief architect in a team responsible for creating an online reservation system for a chain of hotels. The system should encompass features such as guest registration, room availability checking, booking a room, processing payment, and viewing reservation history. Use case diagram. The question is asking to craft a use case diagram for the online hotel reservation system. Your diagram must at least comprise the following actors: guests, system payment service, and the hotel manager. Details the primary functions that each actor will carry out. Let's pause the video for a moment. Take your time to read the question carefully and think about different use cases that could be involved here. Reflect on what we discussed today and try to identify relevant concepts that can help you answer the question. Once you are ready, resume the video and we will go over the solution together. As you see here, drawing the use case diagram is not a tough mission here. This is the most easiest diagram that we covered today. And even I passed to you a clue, which is the actors. We have guests, we have system, we have hotel manager, we have the payment services. And we have different use cases like submit feedback. We can understand that submitting a feedback is something can be done by a guest or by hotel manager. Again, I will accept a lot of different diagrams and a lot of variations, but based on your assumptions that you have to tell me about it. I mean, that should be associated with that diagram. Booking a room, we can understand that booking a room can be done by a guest or by the hotel manager. Platform registration, check room availability, process payment. We figure out that the one that can do payment is only guests here. The hotel manager can update room availability, and he's the only one that can do that and can manage the reservation as a manager. Payment service can validate payment, complete transaction, confirm payment. For a system in general, can display the room details, send confirmation, and store reservation. The second question is about class diagram. Illustrate a class diagram for this system, pinpoint the essential objects, classes, inherent in the system, showcasing their attributes, methods, and the relationships among these classes. I can see these 5 classes, which are guests. In guest, I can see attribute like the guest ID, name, email, password, the details related to the guest. We can have some methods like registrar, check availability, book room, view history. For room object, I can see the room ID, the type of the room, price, status, whether available or not. And we can have some functions like get details of the room, check the status that will return the status. A reservation. In reservation, we'll have a reservation ID, guest ID that did this reservation, the room ID associated with this reservation, date of the reservation, status of this reservation, whether confirmed or still pending. We have these functions, make reservation, get details. For payment, we have a payment ID, guest ID that did this payment, the amount of the payment, payment method, whether credit or debit, the status of the payment, does it pass, succeed, or fail. We have this function, process payment, get details. And finally, for hotel manager, we have the manager ID, the name, the contact information. And we can have this function like update room details or view booking. Of course, this is not a complete class diagram. Why it is not a complete class diagram? Because there is something missing. What is missing? The missing part is the association. How these classes interact together. That's all the classes we have. So let's think together about how they are associated with each other. One potentially misleading association to consider is between the guest and the room. You might initially think there is a direct link between the room and the guest. However, in these implementations, the connection between the guest and the room is actually made indirectly through the reservation object. This ensures that all bookings and room assignments are properly managed through a structured process facilitated by the reservation object. The first link to consider is between the room and the reservation. What is the association here? It is clear that the relationship between the room and the reservation is many to many. A single reservation can include multiple rooms, such as when a large family needs several rooms. Conversely, a single room can be associated with multiple reservations, although these reservations would occur on different dates. The connection between guest and reservation object. I believe it should be many to many relationship. This makes sense when we consider that the single guest can make multiple reservations over time, and a single reservation can involve multiple guests, such as the case of family booking or group stays. The connection between the guest and payment. I can consider it as one to many associations, as a single guest can make multiple payments, but each payment is linked to only one guest. Moving to the link between reservation and payment. I view this as one-to-one association, where each payment corresponds to a single reservation and each reservation has one payment. However, I want to emphasize that some of you might disagree. suggesting that the relationship could involve multiple payments for one reservation, perhaps split payments or using different cards. That's a valid perspective as long as you justify it. Keep in mind that we don't set these rules. It is the hotel that defines them. Lastly, the link between the hotel manager and the reservation. I assume that not all reservations require direct managerial oversight, as many are handled through automated systems or centralized booking service. This is why I assume zero or many. Managers typically involved only for specific cases, such as VIP booking or complex arrangements, whereas standard reservation may not need their involvement at all. So we can see that reservation, maybe I don't have any managers at all, or one in case of the VIP. This is why it's 0, 1 at the manager side. And at the reservation side, I can see zero or many, because this manager can have multiple reservations at oversight or no at all. Construct a sequence diagram to showcase the interaction between the system and its guest when carrying out a particular task. For example, booking a room. Ensure to encompass all pertinent objects and the order of messages exchanged. Let's draw a sequence diagram to illustrate how interactions occur within the booking process. Let's look at the actors and objects involved at the top. We have the guest, the reservation object, the room object, and the payment object. Each of these has a lifeline represented by a rectangle above the dotted line, which shows their duration of interaction in the process. I will start with the guest rectangle since he will be the first one to evoke the interaction. The guest will send a synchronous message to the reservation object to initiate the book a room method. The reservation object then sends a message to the room object with the check available rooms method. The room object responds back with a list of available rooms, shown here with a dotted line to indicate a return message. The reservation object then displays a list to the guest. Next, the guest will select a room and send their payment details to the reservation object. The reservation object will forward these details by invoking the validate payment method on the payment object. Once the payment is processed, the payment object returns the validation result shown with a dotted return line. At this point, we enter an alternative box or alt box that represent two possible outcomes. If the payment details are valid, the reservation object will send a confirmation message, a message to the guest. If the payment is invalid, the reservation object will display an error message back to the guest. This step-by-step flow provides a clear example of how different actors and objects communicate, using synchronous and return message to complete a process. It also highlights the use of conditional paths, represented by the alt box here, which help to manage alternative outcome within the interaction. And that wraps up our video for today. We have covered a lot of ground walking through the core concepts of system modeling and the different types of models, such as context models, interaction models, structural models, and behavioral models. We also understand how these models help us understand, design, and communicate system requirements effectively. Thank you for watching the video, and I hope you found the material helpful. Until next time, keep practicing and refining your modeling skill. See you in the next video. Bye bye.